Hello everyone, my name is Paige Nielsen, and today I'm going to be talking to you about my microbiology project that I've been working on this summer. The structure and mechanics of biofluids can often have broad implications for medical technologies. Bulk rheology is often used to characterize the mechanical properties of fluids in response to external stimuli. However, when examining heterogeneous cellular microenvironments, rheological characterization at smaller length scales is needed to probe their local properties. To indirectly study the mechanics of natural biofluids, which are often difficult to obtain, we can use non-Newtonian biomimetic polymer fluids such as the methylcellulose in this SEM micrograph and investigate their viscoelastic properties using microrheology. Some polymer solutions that we are studying include methylcellulose, which is an analog for the vitreous humor, xanthan gum, which is an analog for blood, and polyethylene glycol, an analog for the extracellular matrix. Here we investigate the differences in results from two different types of microrheology, active and passive. Passive microrheology utilizes small colloidal tracer particles embedded in a fluid and relies on thermally driven Brownian motion to measure its properties. Active microrheology relies on an external force, such as a magnetic field or optical laser, to drive the particle against its environment and measure its viscosity. Magnetically modulated optical nanoprobes, or MagMoons, were chosen as our active microrheological method. 4-micron ferromagnetic beads, such as the one in this SEM micrograph, were actuated in a rotating uniform magnetic field in water, glycerol, and methylcellulose. Utilizing the electromatics in the condensed matter sciences facility of the MagLab in the range of 1 to 10 millitesla, the field was generated using a magnetic coil system. Microscopy videos of the probes were captured using a high acquisition rate camera and then analyzed using ImageJ and MATLAB to find the critical frequencies, or the frequency at which the bead rotation becomes asynchronous. After using water as the control to find the magnetic moment, the critical frequency can be used to find the local viscosity of the fluid using this relationship. Multiple particle tracking was chosen as our passive microrheological method. Hundreds of fluorescent beads were dispersed in these fluids, and their Brownian motion was recorded and subsequently analyzed using the TrackMate ImageJ plugin and Python code. The slopes of the particles' average mean square displacement were then related to the fluid's diffusion coefficients using this equation, and then the viscosity was measured by plugging that parameter into the Stokes-Einstein equation. Using passive microrheology, our results were calibrated against the tabulated bulk rheology data for glycerol as shown in this first graph right here. Notice how a higher percentage of glycerol results in both a higher viscosity and a shorter particle track, meaning that the probe explores less area the more viscous the fluid gets. While passive methods matched bulk values for Newtonian fluids, such as glycerol, active and passive results differed when characterizing heterogeneous biomimetic fluids, such as methylcellulose, as shown in the second graph. In summary, here we use two microrheological techniques to characterize the viscosity of biomimetic fluids. This work with magnetic probes aided in the MagLab's mission to advance magnet technology, and it is significant as it shows that active and passive techniques can provide different measurements, and thus care must be taken when choosing one method versus another. Future studies could involve measuring the microrheological properties of natural biofluids. Spatially resolved rheological data obtained from these techniques can aid in the development of new mechanically tuned biomaterials, disease diagnosis, treatments that utilize mechanomedicine, and nanorobots for biomedical applications. Thank you all for your time. I'd like to thank my wonderful mentors, David Quashie Jr. and Dr. Jamal Ali, and Dr. Hughes for making this MagLab RU possible.